We're discussing the energy equation, and we're going to take some time to see how it applies to things like generating electricity from wind or from hydroelectric hydroelectric power. But before we continue discussing the energy equation, let's do an example. This example is also an example that appeared in a midterm exam. In particular, this was the fall 2009 midterm exam. So I'm sort of doing some of these as we go along, so that you get confident with the type of problems that you will see in the exam. It should be you should find it hopefully a reasonable problem. So take a moment to read that and take some notes about the problem. Hi there. Take a seat if you find one. Everybody's read it and taken down some of the data that's provided there? Okay, who feels that they know how they would start this problem? If you were in an exam now, what would you write down first? Bernoulli equation. Very good. We could do that. So obviously we're being given a station to use here, which is already labeled 1. What's going to be your other station? That's one option, but let's see what we're being asked and what do we have available. Well, let's do that. Yeah, let's do just the jet. Let's call it just jet. Any station here in the jet will be our number 2. Jet. Okay. So let's write down Bernoulli equation between that station 1 and the jet itself. So P1 plus 1/2 rho V1 squared. I immediately am going to neglect differences in elevation and write, this is a free jet, so it's an open jet, therefore I'm just going to write P0, indicating that is atmospheric temperature there, pressure, and 1/2 rho V jet squared. Okay, we don't have any of those velocities, but we do have pressure. There, we have the pressure at section 1, and P0 is just atmospheric pressure. And so let's rearrange this a little bit and write P1 minus P0. Of course, here we are assuming incompressible ideal flow, and we are assuming Z1 equals Z jet, and of course P0 is atmospheric. So P1 minus P0 is equal to, I could write it 1/2 rho times V jet squared minus V1 squared. So far so good? What would you do now? Conservation of mass. Very good. So conservation of mass, or continuity, will help us deal with these 2 different velocities, right? That we don't have there in this equation. So let's just write in the simplest possible way, A1 V1 equals A of the jet, V of the jet. Now we look back at our diagram and we realize that we're actually given the diameter of the pipe and the diameter of the jet, so we're in good shape in that sense. We can immediately rearrange these things a little bit. Or in fact, I might even want to do this. From this one here, I'm going to write rho half V jet squared times 1 minus V1 over V jet squared. Is that good? And now I can take V1 over Vj from this guy. V1 over Vj of jet is equal to the area of the jet divided by the area 1. And now that I can use the diameters almost directly there and save me some writing some pi's and things. So basically the ratio of the areas is going to be the same as the ratio of the diameters squared, dj over d1 squared. And when I put it in here, so back to I have P1 minus P0 atmospheric, I already could put some numbers in there, is equal to rho half V jet squared, 1 minus, and I have d jet over d1 to the 4th power, right? Because the velocities are already squared. So now let's see, we have everything there except Vj, is that correct? Because the diameters are known. What is that little thing I did there? It's a little, oh, it's a dot for my J. Sometimes it's hard to make a dot in the tablet. So the diameters are known, rho is rho of the water, the pressures are known, so we can do this. P1, 110 kilopascal, atmospheric pressure is 101.3 kilopascal, and that is equal to our rho of the water. We could look at this, say it's 20 degrees Celsius, and so rho of the water, we can look it up, 998 kilograms per cubic meter divided by 2. Vj squared, 1 minus, and the diameters. Now it doesn't really matter what units I have the diameters in. I don't have to make conversions because since I have a ratio, that's basically, the ratio is always going to be dimensionless. So I can just write 4 over 12 here, because any conversion to convert that into meters would cancel out. So I just make my life easier and write 4 over 12 in centimeters. The units cancel out. And this is to the 4th power, the diameters. And I can simplify this a little bit and write 1/3 to the power 4. So I can calculate that very easily now. And I can do this. Remember to turn it into, so this is 110 minus 1, so it's 9 minus 0.3, 8.7 times 1,000, 700 Pascal. That's our difference. We now multiply by all of these numbers and we can get Vj. Right? So from here we get Vj, and I have the result right here. Well, it's going to give me Vj squared and I have to take square roots. But I get 4.2 meters per second. So now we've gotten a result. We've applied all the equations that we wanted to, and we go back and read the problem again and see what they're asking, okay? And we go back and say, okay, they're asking for the mass flow in kilograms per second. And I have the velocity. So what we really want now here is m dot. Mass flow is rho a v. And so we have to go back and either use, well, we already have the velocity of the jet, so let's use the jet. We have the area of the jet, and this is just water, so we have rho, and we have A, and we have V. So we can put all of these things for the jet and get mass flow rate with this 4.2 that we just obtained. Any other questions? So let's see. I'll just give you the answer here, and you can check this in your own time. And we multiply back by rho, and we'll multiply by the area of that jet, and we get 5.27 kilograms per second. Now we need to get the height of the fluid in the stagnation tube. And so we basically have the situation that we discussed previously, where at the stagnation point, of course, all of the dynamic pressure will be turned into this height of fluid here, right? And if you recall that, I mean, you could either have it in your notes directly or work it out. Hopefully you, by the time of the exam, have gone over your material such that you know exactly how to get, you know, the dynamic pressure. And dynamic pressure here would be, so H would be, the height of the column of liquid normally would be the same as the equation. So we divided by gamma, basically, our Bernoulli equation, and it was V squared over 2G. That would be converting all of the dynamic pressure into the height of the column of fluid. You could be precious here and add 1/2 of the diameter, because that's the, it's a very small contribution. So you could add the radius of the jet, if you want, plus radius of the jet. It would be correct, and it'll give you a little bit of a difference. And what I get here for that final result is, with the radius of the jet, which is 0.02 meters, I get 0.92 meters. So you see the radius of the jet did give you like a very small contribution there. So what do you feel about this problem in terms of a midterm problem? Does it seem fair? It's fair if you're well prepared, if you have done similar problems, and you know, you're ready to apply your Bernoulli equation and continuity equation in confidence, and don't get carried away by distractions. Like, this is actually the, I don't know if you recall at one point when we were looking at, you know, discussing the ideal gas law, and I said that ideal gas law applies for gases and not for liquids. Well, in fact, this is the problem where one student decided to apply the ideal gas law and try to solve it that way. And I think that it might have been because the information given here about temperature and pressure must have some, you know, a person who's not well prepared just conjures up this sort of strategy which takes them on the wrong path, of course. So it's a fair problem if you're well prepared and have, you know, the things easily found in your notes and so on. Remember, it's open book, and have done, you know, a handful of examples or exercises of the same sort. In addition to homework examples, you can also attempt other exercises on your own, of course, when you prepare for the exams, right? Okay, so now let's go back to what we were discussing, the energy equation. And if you recall, we wrote the energy equation for a control volume by saying the change in energy for the controlled volume is going to consist of two contributions. One contribution is basically the net change with respect to time in the controlled volume of the energy, and the other contribution is the net flux across the control surfaces, that is energy in and energy out. And all of that corresponds to the complete change of energy, which must be balanced by the heat, net flux of heat, and net flux of work in the control volume. So then we went on to discuss the different forms of work. So recall the energy that we're using here, the definition of energy is internal plus potential energy and, kinetic energy and potential energy in this form for the fluid. So then we went on to discuss different forms of work that could be done in a fluid system. We said there's pressure work, there is shaft work when you have the fluid interacting with rotating machinery, and viscous stresses also can do work, but we said, well, we're going to often be very happy and comfortable with selecting our control surfaces so that they're perpendicular to the velocity. And if they are perpendicular to the velocity, then there are no tangential forces that we need to account for. So in general, this we're going to be able to write as equal to, well, we just leave the term of heat, which we often won't have in our fluid systems, but they're considered adiabatic, but we could have different forms of work. So we write the shaft work to indicate a rotating machinery, pumps or turbines, and the pressure work. And for the pressure work, we derived at the end of last class what it would look like, and it is a integral across the control surfaces of pressure, V dot N, the normal, then unit normal, outward unit normal, and differential of area. So what we can do now is, for fluid systems, we know that often in mechanical engineering systems, what we will have is precisely a fluid interacting with a rotating machinery. And so we'll take the pressure to the other side of the equation and put it together with this integral that has the control surfaces already. And you see, we can write the full term-by-term expression of the energy, and then the equation becomes a little bit more adaptable to our situations in fluid systems. So we still have the unsteady term, which often we can cancel out, but for the fluxes across the control surface, we're going to write the full energy in the form U, and let's put plus, we are multiplying by rho over here, so I have P over rho, if I put it inside a parentheses, and I have plus V squared over 2 plus GZ, and I multiply by rho now, the rho that was here in my previous form, V dot N dA. And that is equal to Q net in, and the shaft work, plus, it's a bit messy, let me fix it, which is, of course, usually what we're going to be either given or looking for in terms of rotating machinery. We want to know the work to obtain a torque or an energy being generated by the system, say in a turbine, in a hydroelectric turbine, and so on. So this is going to be the useful form of the energy equation that we're going to often use. And let's see how that can be used in applications immediately. So like we did for the continuity equation and the Bernoulli equation, let's look at the simplest possible system again. The simplest possible system is something that just has a one inlet, one outlet, and is in steady state. That's the simplest case. So let's consider that. So many times, let's see in applications how we simplify, first of some tips or ideas of how we simplify the usage of this energy. First, often we have steady, the situation is steady. And that means that every partial derivative with respect to time that we deal with is 0. So the first term is gone. Second, as I've said often, we want to simplify this surface integral as well. And we note that, of course, this term of the surface integral is non-zero only where the fluid crosses the control surfaces. And in addition to that, we can often safely assume that these terms that appear inside the surface integral, such as u p over rho v squared over 2 and gz, are uniform across the control surface, and so that simplifies quite a lot that flux term. And then finally we could have the simplest possible case of one inlet, one outlet. So what would that look like? 1D flow is what we mean. 1D steady flow is the 1D steady flow, simplest possible situation. So we have something like, you know, a control volume with one inlet, one outlet. And that immediately simplifies our continuity equation, because if it's in steady state, then m out, the m dot mass flux out is equal to the mass flux in is equal to just m dot. And so now the energy equation simplifies quite a bit. So let's separate by so the whole term, the whole integral that we had, Cs u plus p over rho plus v squared over 2 plus gz. Can you see okay with that green? Yeah, it's not too bad. Rho v dot n dA. All that term now we can write as basically u plus p over rho plus v squared over 2 plus gz times m dot out, all of this out, minus the same thing, u plus p over rho plus v squared over 2 plus gz, m dot, but in. So, being very clear, this is our control volume, and the integral across control surfaces is only non-zero where the fluid crosses the control surfaces. So these two are the only surfaces where those integrals are not zero. Our velocity is perpendicular to the area, and so this v dot is just v with their appropriate sign. And we have rho v times a, which is mass flux. And so all of these things are constant across the cross-section, and so they all come outside of the integral, and we basically just have the flux of all of these quantities multiplied by mass flux out and minus in. And that is just... So now we could combine all of these terms together in an application, we could have, if we have all of these assumptions, 1, 2, and 3, then our energy equation is m dot, so it's steady. I don't have that term steady. And so let's suppose that we have, let's just call it O for out, U for in. So we have U out minus U in plus, remember that's energy, internal energy, P over rho out minus P over rho in plus V out squared minus V in squared over 2 plus G times elevation out minus elevation in, and that all it has to be equal to Q dot net in plus the shaft work done by any rotating machinery. So that is a very convenient form that we can now use for fluid systems. Any questions? Okay. Now sometimes we even combine these two and use the definition of a thermodynamic property called the enthalpy, and this is defined by little h. Little h is equal to U plus P over rho, and this is very useful in several situations, especially compressible flows, and this is the enthalpy. And so we write the energy equation. Now we are going to have enthalpy, velocity, and elevation. So let's look at an example, okay? This is a very classical example where we want to use the energy equation, and we can get very useful information. So the question is, so we have suppose we have a steam turbine generation, and the question is how much power are we able to obtain from this system, basically the work output, and we're going to be interested in expressing that as the work output per unit mass. And so what we have here is steam entering the section 1 with properties that are given here. Velocity is 30 meters per second. The enthalpy at station 1 is 3348 kilojoules per kilogram. So units of energy per unit mass, of course. And we also have steam leaving the exit of the turbine. Usually that's going to be like a mixture of steam and water. It leaves with a velocity of 60 meters per second in section 2 and an enthalpy of 2,550 kilojoules per kilogram. So we have steam coming in, doing something, interacting with a turbine in there, but we don't need to worry about the details because we're just going to build a control volume. And so everything that happens inside the control volume is like a black box. But we know that there's some shaft work being done that comes out of this system, and we need to consider that. So to be able to solve this problem, we're going to first assume that it's adiabatic flow, so there's no heat transfer. Q dot equals 0. Oh, I think I was using capital Q. Same. Also, we're going to assume no changes in elevation. and we want to find the work output rather than work output per unit mass. So first of all, we choose a control volume that includes the steam in the turbine from sections 1 to section 2. The control volume encloses anything that's happening in there in terms of the turbine. We don't have to worry about that. And we have power coming out of that control volume in the form of this rotation, if some shaft that's rotating, and then is probably going to be used to generate electricity, right? So we apply the energy equation. We just wrote it down. It was m dot times. I'm going to use the enthalpy now. So the internal energy plus P over rho, we just write H. And out minus in, so 2 minus H1. And plus the velocity term, V2 squared minus V1 squared over 2. The elevation we cancel out, so I don't need to write it down. Well, I could write it down and then say it's 0. And that is going to be equal to Q dot net in, which is also 0, and plus the shaft work, which is what we're looking for. Now the work output per unit mass is, we normally use just a small lowercase w, and it's going to be equal to the shaft work divided by the mass flow rate. This was a net in, okay? So is this is actually in the sense we already have the signs in the work. So the work in is minus the work out, is what I'm trying to say. Let's operate with this equation, and you see that you can divide over by m dot, and enthalpy is given, velocity is given, and so we can basically calculate everything here. And what I'm trying to say in terms of the work is that W in, work in, is minus work out of the control volume, and that is going to be H2 minus H1 plus V2 squared minus V1 squared over 2. And we know all of these things. These are given. So what I want is W out, which is going to be H1 minus H2. So I'm changing signs with everything, okay? V1 squared minus V2 squared. And now I'm going to be able to write the positive results. Kilojoule divided by kilogram minus 2550 kilojoule divided by kilogram plus, now I have V1 minus V2, so this one is 30 squared minus 60 squared. I was mixing things, divided by 2. This meters per second squared. And when I do this, meters per second squared, that is, and this one is in kilojoules, so I need to be careful here that I have to convert that into kilojoule. And so I have a 1000 here to go from, this is to go from joule divided by kilojoule. so that I can get all the resulting kilojoule, okay? Because, well, you can work out those units, but I need the 1000 conversion factor to equal that over there. So now this is arithmetic, and it gives you 797 kilojoule divided by kilogram.
So in general, is work out positive and work in negative? Or is there no?
Let's see how I could go back to when we did the derivation. Net time rate work done, and okay, the net energy, the net work that we have with respect to a control volume, the thermodynamic convention is that it's possible when it's going in the system. And so in the energy equation, what we have is change of energy is equal to the net energy addition due to heat transfer plus the net energy addition due to work going in the system. Okay? But what we are interested in from the point of view of engineering is extracting work from a system. So in the equation, the work is positive when it's going in because of the thermodynamic point of view. Does that make sense? And so this work basically is positive in the thermodynamic sense. This term here is positive in the thermodynamic sense when it's going in, but it's really going out. So this is going to give me a negative number. I could have done it that way, but I've tried to think it in this way here, where the positive here going in is a negative going out, which is the work that I'm trying to, the result that I'm trying to solve for, the work that I can obtain from the steam generator. Does that clarify a little bit? And so this is actually what is important from the point of view of this being a power generation system, of course, right? We're able to get this power per unit mass of steam going into the system. 797 kilojoule per kilogram. We'll do more examples, and hopefully things will become more and more clear. But now let's take actually a little break, because it's been 45 minutes. Let's just take 10-minute break, and then we're going to continue.